Hi, my name is Sivaram, and today I'll be presenting our work on practical intent-driven routing configuration synthesis at Meta. So this work is in joint collaboration with my colleagues in Meta, and also with Minlan from Harvard and Mirkovic from USC. So there is a need for stable and efficient routing. This is because routing misconfigurations can lead to packet drops, traffic black holes, or service downtimes, which are completely undesirable for large data centers. Traditionally, at Meta, generating these routing configurations was a manually driven effort. This is problematic because it could be error prone because of the size of the network, and it can also be time consuming because we support a large heterogeneous set of topologies. There are a lot of existing BGP synthesis approach which can potentially help in automating this process. However, they have three main problems. First, they do not support to handle dynamic configurations which are required at Meta data centers. They do not help network operators to express conditional policies. And finally, they do not support reconfigurations at scale. Before I get into the challenges in more detail, let's quickly go through the background of Meta topology or Meta data centers in general. So typically, a topology in Meta consists of pods, which consists of rack switches represented by RSWs, and fabric switches represented by FSWs. Within a data center building, there could be many pods, and switches within pods could communicate with other switches in other pods using the spine switches. Finally, a data center could have multiple buildings, and switches from one building could communicate with the switches from the other building using the fabric aggregator switches. Over here, we see FAUU, which stands for the upstream switch, and FADU, which stands for the downstream switch. At Meta, we primarily use BGP for routing traffic. This is because it has features which are rich for traffic engineering capabilities. Using BGP, the network operators would define intent, policies, and configurations. So what are intents? Intents are defined as high-level description of a routing goal. So let's take this running example. On the top right-hand corner, you could see the definition of intent I1, where we have a client which tries to reach to a local service from defined by a path of RSW, FSW, and RSW. The network operator could also define a backup path as an intent, saying if the local service is not available, they could reach out to a global service which is actually present in a different pod by taking the route via the spine switches. Of course, the network operators could also specify the preference among these intents and say that the client should prefer the local service over the global service. Now, these are an example of intents, that is I1 to I3. A collection of intents form a policy. So we could have a policy which has I1 to I3, which is specified by the operator. Finally, a collection of policies form a configuration. Now that we have actually have gone through the background, let's look into the challenges faced at Meta data center. The first challenge is the need to support dynamic configurations in the network. This is primarily driven by the dynamic elements in the network. The first dynamic element are intent changes. Looking back at a running example, if the client actually wants to change the backup path, which originally goes from the spine switches to the fabric aggregator switches, the underlying network should actually support this intent change without reconfiguration. The second and another example of dynamic elements are switch changes. Switches constantly undergo changes due to failures or new builds. So we need to move gracefully away from these switches without disrupting the intents. For example, if this SSW switch comes down for maintenance, the backup paths should still be supported or in the network by taking a different SSW which is available. So there is a need for a routing config synthesis that can handle dynamic configurations, including intent and switch changes. The second challenge is the need to express conditional policies in the network. So network operators sometimes would like to apply intents to very specific switches in certain states. Switches at Meta data centers exist in three different states. The first state is a live state, indicating that the switch is operational and is ready to carry production traffic. The second state is a drain state, where the switch is brought down for maintenance and it's not carrying any production traffic. And the third state is the warm state, which is an intermediate state which prepares the switch to be switched to the drained state. Now, the network operator could actually specify intents which are unique to these device states. So going back to a running example, consider intents I4 and I5. So intent I4 specifies that a switch should stop announcing to its peer if its peer is in a drained state. Of course, here, the network operator can also specify preferences based on the device state. So this is specified by I5, which says that peers in warm state should be less preferred than peers which are in live state. Finally, network operators would also like to specify exceptions to some policies. So if you consider our policy I4, where the network operator said that not to announce any to any device, any peer device which is drained, the exception could be to exception to this could be to support loopback interface reachability, so that the device could actually be accessible during management. So there is a need for the routing configuration synthesis that actually allows network operators to express these conditional property policies. Finally, the third challenge is reconfiguration at scale. Reconfiguration of switches can be time consuming. This is because we need to divert the traffic away from the switch, bring the switch down, change the config, and bring up the switch again. On average, this process could take about 4.5 hours, and in worst case, it could take up to 20 hours. This problem is actually made worse given the scale of our network. Many data centers have more than 100,000 switches, and on average, a policy change could affect up to 25% of switches in a particular region. This is going to get only worse because we are introducing new data centers, and we expect the number of switches to double every 5 years. So again, there is a need for the routing config synthesis to reduce these reconfigurations. So we introduced Aura, which is a routing config synthesis at Meta. Aura minimizes reconfigurations by defining base paths or network graphs to pre-configure the network to support multiple policies at the same time. Aura supports dynamic configurations by introducing staging and labeling to choose intents based on certain conditions specified by network operators. Finally, Aura introduced a new language called RPL, which allows network operators to express these conditional policies which I described earlier. So let's look into how Aura deals with minimizing reconfigurations via base paths. Base paths can be defined as a collection of paths. Base paths have this property that any propagation path in the network can be expressed as a base path or a subpath of the base path. Our insight on our idea of base path stems from two key insights. The first one is that base paths can not only support the preferred path, but can also support the dynamic scenarios such as link failures. This is only made possible because of the structure of the data center topology, which are usually hierarchical, symmetric, and uniform. So let's look into how Aura generates the base paths. The first step is via topology simplification, where we abstract multiple switch into single switch nodes based on the roles. In this example, I have represented individual switch roles to a single node. However, this abstraction should be done at the right granularity so that we support enough policies and intents. Here, what we observe is that the granularity is expanded to support intent I1 and I2, which is the running example where I1 is where the client tries to access a local service, and I2 is where the client tries to access a global service. Once this is done, that is after considering the primary path, Aura also considers dynamic scenarios such as link or switch failures to come up with more base paths. For example, consider switch and link failures in the right-hand side of the figure. The blue primary path could actually not work if these devices and the links fail. So Aura comes up with alternative base paths which could actually support the blue path as well. So Aura uses these base paths to support several propagation paths that will cover many intents and policies which could be pre-configured in the network. Now that we have seen how multiple policies can be supported via base paths, we need a technique to identify to dynamically switch between these policies. Aura implements Aura implements this by loading the switch with multiple policies. Now, each policy would have a condition which is specified by the network operator, and only when the condition is satisfied, that portion of the policy is actually activated. So let's take an example. So in this example, we have the network which has implemented both the old and the new policies. The old policy is represented by blue, and the new policy is represented by red. Now we have two prefixes, prefix 1 and prefix 2, which have subscribed to the old policy. Now, the network operator could actually specify a condition to say to match on prefix 2 and switch to the new policy. Similarly, they could say to match on prefix 2 and 1 to switch from the old policy to the new policy. Aura identifies conditions via labeling. Remember, conditions are required to identify which policy to trigger. Typically, conditions are expressed via labels, which indicates the state of the switch or which policy to implement. In this case, let's take the example of the state of the switch. Again, I'm representing the intent 1, where the client is trying to reach the local service within the same pod, and intent 2, where the client tries to reach the global service which is present in a different pod. Now, according to intent 3, the client should prefer the local service over the global service. But consider this scenario where the RSW switch is drained. So how will the client know to take this particular decision? This is done via labeling, where the device would actually mark its announcement with the drain tag and pass it along downstream to the client. Now the client would use these tags from both the intents and take a decision on what path to choose. Now remember, intent I4 says that if there is any, only the live pairs are preferred over the warm pairs. The global path will be now preferred over the local service. So Aura supports the dynamic configuration via staging multiple policies and dynamically switches between these policies via labeling. Finally, we have Aura introduces RPL, which stands for Routing Policy Language, which is based on ANTLR to allow network operators to express these conditional policies. RPL allows network operators to have a broad range of scope definitions. That is, they could define policies based on roles, or they could define policies based on individual switches as well. They also allow operators to specify the different device states and define different intents or policies based on them. Finally, they also allow dynamic configuration, that is, identifying different policies within one single configuration and allowing them to switch based on certain conditions. In this example, we have defined two different policies, which are RSW reachability and allow infrastructure. So Aura allows this expression of conditional policies via RPL. Please have a look at our paper for more details with RPL. So now that we've seen how Aura deals with the three challenges, let me quickly go through the compiler implementation. Aura makes use of BGP community tags to support the implementation of base paths and also the dynamic configurations. For base paths, it makes use of reserved community tags called pathcom and stopcom, and a combination of them are used to implement the full base path or the subpath of the base path. The way it does it is that it matches on a combination of these pathcom and statecom and takes pathcom and stopcom, and then takes appropriate decisions on the propagation of the particular intent. To support dynamic configuration, Aura makes use of another reserved community tag called polcom and makes use of the BGP goto statement to activate portions of the configuration. The figure on the right shows an example where there are two match conditions which matches on two different policies which I covered earlier. The first policy is the RSW reachability policy, and the other one is the allow infra policy. Now, based on the tag, what Aura would do is that Aura would point the execution to that portion of the policy, thereby activating that policy. Aura has been rolled out to about 5 data centers, and more data center regions are being currently rolled out. In the period of September 2021 to September 2022, Aura has been used to generate 54 versions of configurations with more than 800,000 policy versions. Aura has greatly reduced operational burden. This is easy to compare because we have regions which do not support, which are not being onboarded to Aura, and regions which are using Aura. So the way we compare is the total time it actually takes to review these policies generated by network operators. What we find is that non-Aura region takes 8 days to evaluate, whereas Aura region takes half the time. We also notice the number of revisions, that is the back and forth which is required between the network operator and the reviewer based on the region. What we find is that non-Aura region actually takes 3 times more revisions than Aura region. This is because the representation of RPL is very simple and it's more easier for network operators to use. So in summary, we present Aura, which is a routing synthesis framework at Meta, which is capable of reconfiguring switches at scale via base paths. We handle dynamic configurations via staging and labeling, and we allow network operators to express conditional policies via RPL. Aura is actively running in Meta and has reduced operational burden. Our paper has more details on routing verification, more evaluation, operational research, so feel free to take a look at it. And we do have some people from Meta here, so you can reach out to us and ask us questions, and also Minlan is here as well. So thank you for your time. If you have any questions, I'll be happy to answer.